Center of mass. All the problems we've solved have assumed that we're dealing with point particles even when they involve sleds, cars, and buckets. This is shown most clearly when free body diagrams were used to find the acceleration of objects due to multiple forces. The object was actually represented by a point. Other than making the problem simpler, which is good, why did the computed answers actually match what happened to the larger, more extended object? Simple solutions are no good unless they represent reality. To answer this question, the center of mass will be defined and its relationship to the conservation of momentum will be shown. Start with a two-dimensional system, over here, that can either be a number of independent particles, which were shown here, a large extended object such as a car, or several extended objects. The linear motion of the center of mass of a system in response to an external force is the same as if the total mass of the system is concentrated at one point, which is the center of mass. So here we have an external force on this system of particles. We have the same external force over here. And what is that? That's our center of mass. Right here is center of mass of all these different particles. So we put that over here, and we consider that the total mass of all the objects is this symbol right here. You add all these together, and this force and this force are the same, and this object here acts just like that entire system. The motion of the individual particles does not match the motion of the center of mass. Right? This could be going this way, this could be going that way, but when all their motion vectors are added up, they equal the motion of the center of mass. And again, the center of mass is not a real object, right? It just is acting as a stand-in for all these different particles moving in different directions. Calculating the center of mass for a large extended object is beyond the scope of this course. The center of mass is a mass-weighted average. Particles with a greater mass contribute more to the location of the center of mass. The particle in the upper right of the system has the largest mass and will have more of an impact on the center of mass than the other particles. Choose a reference frame to measure the x and y distances between the particles and the origin of the frame. So here's the origin. We'll want to measure this x distance and this y distance. Find the distance between each independent particle and the origin. If it is to the left or below of the origin, assign a negative value. If to the right or above, assign a positive value. The particles in the lower right quadrant both have negative values for their distances from the origin of the reference frame. The particles in the top left quadrant will have a negative x and positive y values. Label each mass with m sub I, x sub I, and y sub I. Define the center of mass as having coordinates x center of mass and y center of mass, where, and this is how you calculate x center of mass. Same thing for y, just replace x with y. So you have the mass of an object times its x distance from the center of from the origin right here, and this would be m2x2, m3x3, and you do that for all your particles. And that's what this symbolism is, the summation of all mi(xi)s. And then the same thing for y center of mass. So let's look at this large mass over here. That's labeled with the coordinates x1, y1, and mass m1. The center of mass is over here. And that we will find out if we were to calculate all these m sub x's, add them all together, divide by the total mass, because that's what this term is, and that would give you coordinates of the center of mass. Find the center of mass of the two masses. The mass at x equals -2 meters is 3 kilograms. The mass at x equals 1 meter is 5 kilograms. We'll choose our origin as x is equal to 0, pretty common, and the resultant will be measured from the origin also. So let's label this first mass m1, this is m2. So our x center of mass is m1x1 plus m2x2 divided by the sum of the masses, m1 plus m2. So we have 3 kilograms for the first mass, And since distances to the left of the origin are negative and distances to the right are positive, we get a negative 2 meters here, and for the 5 kilogram mass, we get a positive 1 meter. Carry out the math, and we get x center of mass is minus 0.125, and that's this red dot right over here. Similar to the center of mass of the system, define its velocity as follows in vector format. The velocity of the center of mass will be once again a weighted average, where we have m1v1 plus m2v2, etc. And on the bottom, we sum up all the masses. And here's the math equation here. It's a little bit shorter than doing all the m1v1s. Then substitute p for mv, and we get the velocity of the center of mass is the sum of all the individual momenta divided by the total mass of the system. So what do we have now? We're describing the system as one object with one center of mass velocity. This equation shows that the total momentum of a system of objects is equal to the total mass of the system, that's the capital M, times the velocity of its center of mass. The system acts the same as if all its mass was concentrated at the center of mass. We can rearrange that to solve for the velocity of the center of mass. That would just be the momentum over the total mass. If the momentum of the system is constant, that is, no net external forces are acting on it, then no matter what the individual objects are doing, the velocity of the system's center of mass remains the same. In a system of objects, both internal and external forces are present. Internal from the interaction of the objects, and external coming from outside the system. So we can write the sum of the forces is the sum of the external forces and the internal, and that will be ma center of mass. Now let's use Newton's third law. The internal forces are action-reaction forces, and their net effect on the system is zero. So the sum of the internal forces is zero, and that leaves us with this equation right here. This enables us to work with solid macroscopic bodies, which is what we talked about when we first started this topic. The body accelerates as if all of the external forces are acting on the center of mass of all its component parts. The photograph shows 3 fireworks rockets. The center of mass of each rocket kept moving up, and the particles symmetrically spread out from each one. For each rocket, the velocity of the center of mass is equal to the weighted average of the velocities of each particle, resulting in the starburst pattern. The acceleration of each particle after the explosion and the center of mass, of course, all equal negative g. Even though the center of mass velocity and acceleration is the same before and after the starburst, the individual particles are moving in many directions. But the vector sum of all the particles' velocities and accelerations is equal to the velocity and acceleration of the center of mass.